Hello guys and welcome back to another video. It's been actually quite a while since the last one. And full disclosure, I've been away from this project and from Zig in general for about 2 months. Written quite a bit of Rust and Python in the meantime. But we are back, baby! So let's see if we remember where we left off. Right, so from my roadmap here, I see that we have worked on heap allocation. Actually, we were doing body allocator. Yep. So here it's marked as almost there, but I think we should be fairly happy with where we are now. We have a body allocator that can do allocations and freeze. So we, I think we don't handle resize, body. So I think we don't handle resizes and remaps, but I think that's all right. I think I can live with that. Right. So for this video, I think I'm gonna stay away from the allocation side, and I think I'm going to go to GDT redefinitions, and I'll probably going to take a look at all the at least initializing all the descriptors, so GDT, IDT, and probably take a look at all the descriptors or segments needed for task switching. Yeah, so I guess that's a good plan for today. Let's get to it. Right, so for the GDT, I'm not going to go into details because I think, we have already covered that for our BIOS bootloader. We did have to manually set up a GDT, so I think we've covered the basics. Although here we just went ahead and created this static GDT map, and I don't really think that we are going to stray far from what we did here, so I'm going to leave it at that. But I'm going to actually have to pull out the documentation just so that I can remember how these go. Right, so the way segments work in this, so we can have one global descriptor table, which is GDT, and we can have multiple local descriptor tables so that every process can have its own, I guess, segment descriptions. And the GDT can actually have multiple segments, or rather multiple segment types. Usually they are 8 bytes, so 64 bits long, but we can also have segments that are, I guess, 128 bits long, these ones here, the TSS descriptors. And so do we have any more details here? No, that's very cool. Oh, so actually we do have them here. So these are the types we can set. So let's start by creating a, let's call it descriptors.zeg. Sure. And let's try to think about this. So actually, before we think about this, we should also try to design what we want this to be like. So in my mind, I think I want a sort of struct that will have a so GDT descriptor here, which would have the base address, length, and all the cool things we need to do, as we've seen when we work on this on the BIOS bootloader. And below that, we are going to have n entries, and I think we can decide on having 5 entries because I am not going to make this any more complicated than we've done in the BIOS bootloader. So basically, I just need a kernel code, kernel data. And actually, the first one would be the null entry, which is unused. Then kernel code, kernel data, and user code and user data. Yeah. So 5, and I guess the yeah, these would be just basically constants or just comp time known things. But that's for the GDT part. That's for the memory segmentation part. Then we have other registers that get basically attached to this, and these registers are the task segment descriptors. And basically, let's add that these ones are 8 bytes wide, so all of them are 8. These ones here are 16 bytes wide, and these task segment descriptors will describe things that are called TSS or task switching segment, I think. I'm gonna have to quickly look that up here. So what is TSS? Yeah, so it's okay, so it's task state segment, what TSS is for. Okay, so basically, can we go up? So yeah, this struct here, this huge struct is the, so this one is for 32-bit, but we should have one that's fairly similar for 64 bits. So this task here is the task state segment, and this is used by the CPU to basically store information about tasks. By tasks, we mean processes or threads. And what we would like to have is one such TSS per core, so that we can have every core do its scheduling without impacting the other cores next to it. So that's pretty much all there is to it. And I think if we go back to, not sure if it's here. So this one is for the descriptors, but somewhere they are going to talk about TSS descriptor in 64-bit mode. Yeah, there we go. So this one here is the TSS descriptor, and this here is what the 16-byte struct that gets added to the GDT or LDT. Right. So these ones we need to have, as I said, one per TSS, and we have one TSS per core, so we should have one of these per core. So if we go back here, we can see that we already have the struct for, actually we don't need to do that. We can just go here and yank it from here. I think it's described somewhere, not too far. Well, nice documentation. Okay, should be this. Yeah, segment descriptor. Yeah, cool. So, pub const, let's call it segment descriptor. Yeah, I actually have, let's call it 8-byte segment descriptor 8-byte. Sure. I think in this language we do this. And here we should actually not forget to put this in front of that. And here we should go ahead and take, so segment limit. So limit, let's call it lower. And this one here is what is a 16 bits, so it's a U16. Then we have base lower, I think, which should be a U16 too. And then we'll have a base. Well, actually, we can join those two, I think. So does that give us 16 and 8? So that's 24. Then we have type, which let's do it this way. Type, which is 4 bits, but we'd like to. Do we have types somewhere? Type field. Okay. Yeah, so 4 bits, and they are composed from fields. So I think I'm going to create an enum for that. Let's call it segment type. So segment type, and I'm just going to put this here. Const segment type is an enum that relies on a U4. Sure. Actually, I don't really want this to be an enum. I want this to be a backstruct. And I forgot to put this here. This should be a U64. So this backstruct here would have every single field given here, and those fields would be so A, what is A? Accessed, right enabled, and expansion direction. And what is this other one here? This other one here is it data or code? Or yeah. So is that, yeah, so accessed U1, or I guess bool. I think we are never going to set this access field. Yeah, this access field is CPU set, and we don't really care to set it. So yeah. Okay. Well, we'll have it there, but okay. So right enabled, I think. Bool, and what was the other one? Expansion direction. Expansion direction, which is also a boolean, and the other one is code, which is also a boolean. Cool. So now we have that. So if we go back to God knows where we were before, that should be somewhere over here. Yeah. So S is for the descriptor type. I'll call it system, and I'll take that as a boolean since it's a single bit. DPL is descriptor privilege level, and that's 2 bits. It can be 0, 1, or 2. Oh, 0 to 3. Yeah. Okay. So privilege would be segment privilege level. Yeah, let's call it that. And here, let's go for pop const segment privilege level. Actually, yeah, I'm just going to do something here. U2, and I'm going to remove segment from all of this, all of these, and I am probably going to create pub const segment is a struct, and just going to wrap all of these in that struct. Yes, sorry about that. Cool. Segment type would be just type, and this one here would be just there we go, privilege level. And here privilege level will have so 0 to 3. And I guess we should do ring 0. I don't need this. Ring 1 is 1, and ring 2 is 2, and ring 3 is 3. A bit useless, but whoops, there we go. A bit useless, but we are going to roll with it. Actually, what we need is probably just ring. I could remove these two, but okay, there are 4 of them, so no problem there. So that's privilege level. Oh wait, hold on. What is this doing here? Right. So then we have B, which is present just 1 bit. Boolean, and then we have the segment limit. So the upper limit, and this one is 4 bits. So that's 24 bits for the limit total. So limit, limit upper, and that's wait, did I say 4? No, did I say 24? That's just 20. And then AVL is AVL available for use by system software. Yeah, sure, we are not going to touch this, I don't think, so let's leave it at that. L is, I think we should give it a better name. I guess we should call it something like E64-bit. Sure. And then the remaining one is EB. Default operation size. Let's just call it size. And that can be 0 or 1, so that's U1. Sure. And we have granularity, and that's a U1 also. No, actually that's not a U1. That should be some sort of enum. Granularity. Yeah, let's go somewhere. Let's group the enums together. Const granularity is enum over U1. And here we have, I think there are just 4K or, yeah, so bytes or blocks of 4K, yep. Bytes is when it's set, when the granularity field is clear. Okay, so that's 0. Pages 1. Cool. And here we'll have just the rest of the base. So what would that be? That's like 8 bits. So base upper, and that's a U8. Okay, let me just compare this with what we had in start ESM. Let me just open this here. So we have limit, base. Oh yeah, of course, we've grouped these two. Yeah. So we had limit, base, and then we had access flags. So here we have 8 bits of them. So let's see. This one is 4. This one is 2, so that's 3, that's 8. Yep. And then we have access bits. So that's present 5, 6, 7, 8. And then we have granularity. Oh wait, hold on. What is type? Type is 4. System is 1. And privilege level is 2. So that's 7. And then present is, oh yeah, okay, that's cool. So that's 8. That's access flag. And here we have a combination of flags and limit. So here we have limit as a U4, and we have 4 bits of flags. So 1, 2, 3, and 4. Yep, and then we have the base. Cool. So we did this correctly. Okay, so that's the 8 bytes descriptor. So let's also go ahead and get the descriptor cryptor 16 bytes. And I don't know why I put S here. Is a backed struct, this time of a U128. We'll see how that goes. Right, and here I'm going to need to go and find it. I think we should have a link somewhere. Right. Segment descriptor tables, that's where we came from. TSS descriptor, that's where we want to go. In 64 bits, and that's what it looks like. So basically we have the same structure on the lower 8 bytes. We have the same structure as the GDT, but we have an extension here to add a longer base address, basically. So do we want to reuse the other segment, or do we just want to roll dog this and get a new segment altogether? I think I'm just going to copy this. Yeah. There are a few fields that are have forced values. So I'm going to model that here. So right after type, between type and DPL, we have system here set to 0. So how do we go about that? Let's do false. Yeah. Okay. And actually, I'm going to need to create for every one of these, or rather every one of these two, a constructor. So that basically, instead of having to split up the addresses to these things here, I'll just pass the address to the constructor and we do the split in it. Right, so here between AVL and granularity, we have these ones set to false, and this one here is set to 0, which is like that. And then we have an extension on top of that, which is just 32 bits of base address. And then we have, so I think we can just write zeros there with no repercussions. So let's, so we want this to be 8 plus 32. So that, and then here we're just going to do reserved U32. Right. Yeah, actually, let me force this to 0. And that should do it, I think. That should do it. Now, if we want to make this complete, we could also go ahead and create the task, what's it called? The task TSS, basically, task state segment. If I can find it, I think that's what it should be. So this one here should be the 32-bit task state. And this one here, yeah, this massive thing here is what we need to write. So we have, and also we are going to need to check the alignment requirements, all of these things, just so that we don't have any weird behaviors. So let's go ahead and create const. So task state segment, that's fine. Backstruct. How big is this? Quite big, actually. So I'm not sure we are going to be able to use backstruct. Maybe extern struct would be more what we are looking for. Anyway, we'll see. So we have a reserved, let's call it 0, which is a U32. And then we have the RSPs. And RSPs stand for, do we know? Yeah, so stack pointers. So that's, we'll get into the details of this when we get to scheduling and actually using these structs. But yeah, for now, let's just write it out. So U64 for RSP0, and we want three of those. So RSP0 is a U64. And we'd like 2 more of those, please. There we go. And then here we have a U64 reserved. So reserved 1 is a U64. And we'd like to have an IST, so 7 of those. Each one is 64 bits. So IST1 is a U64, and we'd like 6 more of those. Yeah, and actually, let me just do this and do, there we go. Right, and then 2 reserved, or rather 1 reserved, 2, which is a U64, and some more reserved, so reserved 3, which would be a U16, and then the IO map offset, which would be a U16 also. IOMAP base address. They say it's a base address, but I think it's an offset. Yeah, 16-bit offset to the IO from the TSS base. Okay. Okay, cool. So far, so good. Now, let's try to actually create these things. So for now, I think I'm just going to focus on the 8-byte struct. So pub function, probably not new, let's call it create. And we'll see what we get from that. But this one here returns this. I think that's how we do this in this language. And this should return something like so. So limit lower would be limit lower. Base lower would be base lower, and let's go through all of these. Type would be just type. I think we get that in system is system and privilege. Yeah, sure. Let's take that also as a parameter of that. Yeah, I'm not sure. Let's call this. Let's do something like args dot. Yeah, these ones will compute. That's fine. These ones will want to have get from a sort of args, which would be a struct that will have so base address, which would be a U64. So we have 32, I think, should suffice. Limit would be a U20. Yeah. And then we'll have type, which would be type with a default of I guess we need to create type. How do we go about that? So public function create, and this one here also takes args, which are struct of accessed, which is a boolean that defaults to false, write enabled, which is a boolean, expansion direction, which is also a boolean, and code is a boolean that defaults to false. Yeah, that's a good default. Add this, and this one here returns basically accessed. Yeah, in this language we do this is so args.accessed. It's cool. Write enabled is args.write enabled. Expansion direction is args.expansion direction, and code is args.code. Yeah. Cool. So now let's create here const kernel code is type.create. Access we don't care. Write enabled. So we said that code would be false. Actually, should we do this? Sure, so that's true. Expansion direction will get true, but code is true for this. And expansion, yeah, we are actually going to need that. Expansion direction is, yeah, so what are the values for that? Segments, there we go. And up we go. Expansion direction. That should have been described here. So expand down, and the other one is conforming. Okay, so expand down. Does that mean that it goes up sort of like a stack? I think that's how it should be. Okay. Right, so I think we are going to say false. And I think I'm going to do one better. I think I'm going to go ahead and set this to be false by default. Yeah. And that means we can remove all this. Cool. Oh yeah, this language here does that. Cool, so let me just do this. So here it should be data and, oh, okay, not date. Okay, not that. And this one here needs to be false, so I guess we can just remove everything here. And we can do the same thing basically here, except that we are going to replace kernel by user. Yeah, there's just one of them. Cool. So here we can basically use this type, and we don't have to recreate. We can just use bit of a problem here. This needs to be code is true. And this here needs to be code. Yeah. Right. So then we have system, which is a Boolean and defaults to I think we can make a sane default by saying it's true. Yeah. And then we have AVL, which is a Boolean, and then 64-bit, which is also a Boolean. And then we have size. And I think size, yeah, sure. Okay, size is a U1, and then granularity would need to be granularity, but this one has a default of, what did we say? We'll default it to pages. And that's pretty much all we have to do. So let's do that. Let's add AVL is rx.avl is 64-bit is rx is 64-bit, and size is rx.size, and then granularity is rx.granularity. And then we are just missing base upper, which is base upper. Oops. There we go. So now we just need to compute limit lower. This one would need to be args.lower. limit, and we'll do a few things with it. So base lower is args.base. I call this base address. Let me just call it base. Then we have const limit upper, I think, just args.limit for now. Let's put this together. And base upper is args.base. Base. Right, so this one is not used. Why is that? Because we have not used it. So right after present, which we also haven't used. Cool. So right after privilege, we need present, and that needs to be arg.present. And here we need to have limit upper, which is limit upper. Yeah. And then here, that means that we need to have present. So where should we define present? We also have not defined privilege, have we? No. So privilege. This one here is a privilege level. Oops. And this one here defaults to ring 0. That's good. And then we'll have present, which is a boolean that defaults to true. Okay. It's not too bad. Right, so now let's take a look at what we want here. We want this to be the lower, how many? So hold on, this one needs to be a U16. Oops. Yeah. So this one wants to be a U16. Base lower wants to be a U24. And base upper wants to be a U8. Not 9, 8. This one here wants to be a U4. Yeah. So this one will end it with I guess we could do stud. We need stud then. So how do we go about that? So we do this in this language, import, and we just do stud. Speaking of which, I have seen that there were quite a few updates to Zigmaster and quite a few breaking changes to I still haven't had the courage to port the project to the newest master. Maybe I'll look into it sometime. Is there a better way to go about this? So do we have a trunk? So no. Int yeah. How does int cast work with truncates? So we do have at truncate. So this function truncates bits from an integer, resulting in a smaller or same-sized integer type. Is well-defined and working code. Okay, that's pretty cool. I think that's what we need. It truncates significant bits, regardless of interness. That's all I need to know. Right, so I just guess I need to call truncate base. That's or rather limit is what we want to truncate. And this one here would also work with truncate. The only difference is that we are going to shift it by do we have, so I know how much I want to shift it with, but I want to see if we can get a log from a type. So returns an unsigned int type that can hold the number of bits in t-1. So u16 dot, is there like something in this that I can use? Dot bits. Something like this. If this compiles, this is actually pretty nice. Just need to see if it's okay. So it's not public. It's not going to build. But I think I could do something like type. So this one returns type info. Yeah. So type info of u16 dot int, I think, dot bits. Gonna need to take a look at what type info is. Yeah, so that's that, and in int we have bits. It's pretty cool. So that should work. That means that we are going to move this, shift this by 16 bits, and then we truncate that to be a U4, and that should just work, I think. And we are going to do the same trick here, and truncate this here, but we are going to shift it by. Yeah, we'll do the same thing. So type info of u24, I believe we did, dot in dot bits. Whoops. There we go. And that should just work. Yeah, we'll see about that. It should, in theory, just work. For this here, I'm going to just basically copy this function here. Yeah. And I'm going to yeah, let me do something first. Let me get these and just put them here in segment. And actually I want these to have just type at the end. Yeah. Okay. And here we are going to need, so the only thing we are going to need is that base has more bits. And how many are those? So this one is 24 and 40, that's 64. So the only thing we need to do here is just change this to be 64. I believe. Yeah. So base upper would need to be here defined as U40. And all this should just work out, I think. Cool. Task state I'm going to leave alone for now. So these are the row descriptors. Now we are going to need to build a layer upon this, I think, so that we could say, so basically I want to build a GDT entry, so that behind the scenes would decide that we need a 8-byte descriptor, and builds one. And I could say I want to build a GDT, or rather a TSS descriptor entry, and that should decide that it wants a 16 bytes descriptor, and builds one. And I want all of this to be packaged into a struct that I call GDT, and this struct here would be a sort of header, so GDT header, which would basically have things like, maybe I could show that in here. If they are nice enough to show us what a GDT would look like. Right. Maybe that's too much to ask. No, actually that's fine. So we have the GDTR register, which basically has this form here. It has the base address and the limit. So basically we can model this as a base address and a size to compute the limit. And this is basically, so the address of this struct here gets loaded into this register here, the GDT register. And the way I see this is that we just have to get this header here live somewhere above the list of entries, and that way we can just package everything into a nice little struct. So GDT header, which would be a base plus a limit, and then we have entries, and we'd like to have a way to create these entries here without having to create them one by one. So that's why I've packaged these into this segment struct here, so that I can go down here and create a const GDT, let's call it struct, and in this, let me just put this over here. Okay, and in this struct here, we'll have a constructor, so something like public function create. And this would probably do some memory allocation. So let's think about this for a bit. If we can do self is at this, and here we could probably return a pointer to self. So to do allocate, so as I said before, we are going to need to check the alignment requirements for all of these structs, the segments, but let's for now think about this as requiring a page alignment. Let's allocate page or pages, depending on how big this should be, and then create a basically GDT header, so that we need here I guess we could just pass it base and limit, or rather limit would be computed from the number of items we put in this. And then here, for this, we'll have public function insert segment, something like this. And this insert segment would take a segment type. Or rather, no, we could go for insert GDT descriptor, and we could have something like public function insert TSS descriptor instead of description. And all of these would take self as a pointer to self, which is basically the page we've allocated, or pages if we need multiple of those. And we can go and do stuff like this. And every time we insert one, we basically recompute the limit so that we can, at the end, have a function that goes like pop function. How should we call this? Load? Yeah. And this one here would also take self pointer and returns void. And what this would do is basically call so GDT. What was the? I think we have it here. So yeah, LGDT here. So load GDT gets basically the address of the GDT struct that we want to create. That we have here. Yeah, so this one here is the base address, and this one here. No, this one here is the base address, and this one here is the limit, or basically the size of it. Right, so this one here will be LGDT, GDT, and it loads itself into the CPU. That's, I think, it's not a bad design. And then if we want to have, of course, we'll need also to have the IDT, which we haven't talked about, but for now, let's just go ahead and design it, which would be pretty much the same thing. So I'd like them to have this create and load things here, and this one here would load IDT, except that here we don't have insert descriptors, we'd have register exception handler, and the other one would be register trap handler. And I'll get into detail on what is an exception, what is a trap, in a later date when we work on interrupts and exception and trap handling. And I think I'm not going to push it any further. I'm not going to try to make this any more generic. I'm just going to have this IDT and GDT be duck type to something that has a create and a load. Yeah, that's pretty cool. Well, I think that's a good place to leave it for now. I think the progress is not too bad for a project I haven't looked at for a while. I just hope that you were not too confused by some of the things we've seen. I sure know I was, but these are hardware specific things, and it's fairly hard to develop a mental model for them. They are just things that need to be known. Anyway, that's it for this one. Hope I see you next time. Fucking out.